Now let's take a problem based on GET examinations. So now I am taking the problem which is asked in a GET examination and based on refrigeration. So GET problems based on refrigeration. Refrigeration. So we will discuss about GET problems based on refrigeration. So first I am taking the problem which is asked in year 2009, GATE AMI 2009. I am writing the problem here first. In an ideal vapor compression, in an ideal vapor compression refrigeration cycle, the specific enthalpy, the specific enthalpy of of refrigerant in kilojoule per kg at the following states is is given as inlet of condenser is 283, exit of condenser that is 116, exit of evaporator is 232. Find COP of this cycle. COP means coefficient of performance of this cycle. So here the enthalpy at the various states is given. We have to find out COP of this cycle. So now let's draw the pH diagram for this ideal vapor compression refrigeration cycle for our better understanding. This one is pressure and enthalpy. So the DOM will be like that. And we know this 1 to 2, that is isentropic compression, 2 to 3 constant pressure heat rejection, that is in condenser, and 3 to 4, that is a throttling process, and 4 to 1, that is constant pressure heat addition in evaporator. So this one is the typical process here. And now according to the problem, inlet of the condenser is given 283. So which one will be the inlet of condenser? 2. So here I will write H2 is 283 kilojoule per kg. Similarly, exit of condenser is given 116. So exit of condenser is here, that is exit of condenser. H3 equals to 116 kilojoule per kg. Now exit of evaporator is given 232. So this one is exit of evaporator. So H1 equals to 232 kilojoule per kg. And now we are interested in COP. So for COP we have to find out work done as well as we have to find out Q2, because in COP we are interested in Q2 and W for refrigeration cycle. So now for W, that is WC compression work. So I can say W is nothing but compressor work, and in compressor work it is here it is mentioned H2 minus H1. Here this H2 after compression, before compression H1. So 283 minus 232. So if I do this calculation, 283 minus 232, so it will come 51 kilojoule per kg. So now we are having compressor work. Similarly, we have to find out Q2. But here if you see, at 3 and 4 point, that is constant enthalpy point. So we can write like that for diagram. H4 equals to H3, then H3 we are having 116 kilojoule per kg. So now we can easily find out Q2. So Q2 will be come here for refrigerating effect. So Q2 equals to, here it will be H1 minus H4. So 232 minus 116. So if we calculate this thing, 232 minus 116, so it will come 116 kilojoule per kg. So now we are having Q2 and W. So COP we can easily calculate. COP is nothing but Q2 by W. So 116 divided by W is 51. So 51. So 116 divided by 51. So it will come 2.27. 2.27. So the correct answer for this question is 2.27. Now let's take another problem which is asked in year 2009. So GATE AME 2009 problem. First I will write the problem. An irreversible heat engine and irreversible heat engine extracts heat from a high temperature heat from a high temperature source at a rate of 1000 kilowatt and rejects heat to a sink at a rate of 50 kilowatt. The entire the entire work output of the heat engine is used to drive a reversible heat pump operating between a set of independent heat heat reservoirs at 17 degree centigrade and 75 degree centigrade. Find the rate in kilowatt at which the heat pump delivers heat to its high temperature sink. To its high temperature sink. Now let's solve this problem. So for this problem, I will first draw the block diagram for our clear understanding. Here there are two kinds of system. One is heat engine and second one is heat pump. So the heat engine, whatever work is producing by heat engine, it will use to run the heat pump. So first I will draw the heat engine. So heat engine, that is source for heat engine, and the temperature source is giving heat at the rate of 1000 kilowatt. So here we are having the heat per unit time. So we can say that it is Q1 dot, and this one is heat engine here, and now it is giving 50 kilowatt to the sink, that is Q2 dot. I am putting dot because this one is the heat per unit time and this one is sink, and it is producing a W work. So here if you see, we can easily calculate W here. Now I am drawing the heat pump which is working between 75 degree centigrade and 17 degree centigrade, 17 degree centigrade, and here it is heat pump. So this work the heat pump is using for extracting heat from the 17 degree centigrade reservoir and is supplying to 75 degree centigrade reservoir. So here this one is Q2 and this one is Q1, and our interest is Q1. So now we will put in terms of rate because we have to find out Q1 per unit time. So better we will put Q1 dot Q2 dot. So it will be Q1 dash dot Q2 dash dot. So we are interested in Q1 dash dot. So now first calculate the W. So we know W is nothing but Q1 dot minus Q2 dot. So W equals to 100 minus 50. So W will come 50 kilowatt. That is work per unit time. Similarly here we can easily find out the Q1 dash dot, and here it is mentioning in the problem it is reversible heat pump. So the pump is heat pump is reversible, then we can use COP equals to for pump it is T1 divided by T1 minus T2. That is only for reversible heat pump. And we write reversible heat pump. Heat pump. So here T1 that is 27. If you add 273 here, it will be 348 Kelvin. And the 17 degree, if you add 273, it will be 17 plus 273, it will be 290 Kelvin. So now we are having T1, so I will write 348 divided by 348 minus 290. So 348 and 348 minus 290, it will be 58. So the COP is coming 6. So the COP for this reversible heat pump is 6. So now we are having W. W will be same. We have already calculated. It is 50 kilowatt. So again with the help of COP formula, COP equals to Q1 by W, that is Q1 dot dash by W. So we will get 6. W is 50 equals to Q1 dash dot. So the Q1 dash dot will be 300 kilowatt. So the correct answer is 300 kilowatt. Now let's take in another problem which is asked in GATE AMI 2008. So GATE AMI 2008. First I am writing the problem. A cyclic device operates between three thermal reservoirs thermal reservoirs as shown in figure. Heat is transferred transferred to oblique from the cyclic device. It is assumed that heat transfer between each each thermal reservoir and the cyclic device takes place across negligible negligible temperature temperature difference. Interaction between the interaction between the cyclic device cyclic device and the respective thermal reservoir and the respective thermal thermal reservoir that are shown in figure are all in the form of heat transfer are all in the form of heat transfer. So now I am drawing the diagram here. This one is 1000 Kelvin reservoir. This one is 500 Kelvin reservoir. This one is 300 Kelvin reservoir. And this one is the cyclic device. So it is receiving heat of 100 kilojoule from 1000 Kelvin reservoir, receiving heat of 50 kilojoule from 500 Kelvin reservoir, and rejecting heat of 60 kilojoule to the 300 Kelvin reservoir. So now the question is the cyclic device can be option A reversible heat engine, reversible heat engine, B a reversible heat pump, a reversible heat pump, C an irreversible heat engine, and irreversible heat engine, and D an irreversible heat pump, and irreversible heat pump, reversible heat pump, or an irreversible refrigerator. So now let's solve this problem. Here, if you see, the cyclic device is taking heat from the high temperature reservoir, that is at 1000 Kelvin and 500 Kelvin, and it is rejecting heat to the low temperature reservoir, that is at 300 Kelvin temperature. So the behavior wise it is looking like a heat engine, but it may be irreversible or reversible heat engine. So for calculating irreversibility or reversibility of heat engine, we have to find out total entropy change of the system. If it is coming 0, then it is reversible, and if it is coming more than 0, means it is coming positive, then it is irreversible heat engine. So No, I will find out the entropy change for each component, and then I will find out the total entropy change of the system. So now find entropy change of 1000 Kelvin reservoir. So del S for 1000 Kelvin reservoir. So this reservoir is losing heat, so it is coming negative, divided by temperature, that is 1000, so it will come minus zero point 0.1 kilojoule per Kelvin. Similarly, del S for 500 Kelvin reservoir, it is also losing heat, so minus 50 divided by temperature 500, so again it is coming minus zero point 0.1 kilojoule per Kelvin. Similarly, del S for 300 Kelvin reservoir, so it is getting heat, so positive 60 divided by 300, so it will come 60 divided by 300, so it will come zero point 0.2, so zero point 0.2 kilojoule per Kelvin. And del S for cyclic device, it will be 0, because for a complete cycle entropy will be 0, because entropy is a property and the cyclic integration of any property will be 0. So now del S for universe, it will be summation of all, that is zero point 0.1 plus 0.1 plus 0.2 plus 0, so it will come 0 kilojoule per Kelvin. And if the change in entropy for universe is coming 0, it means it's a reversible. So the correct answer for this question is a reversible heat engine. Now let's take another interesting problem which is asked in GATE 2005. So GATE AME 2005. I am writing the problem here. The vapor compression refrigeration cycle is represented as is represented as shown in figure with state 1 being the exit of the evaporator. State 1 being the exit of evaporator. The coordinate system used in the figure is, now we have to find the coordinate system used in figure is option A, pH diagram, option B, TS diagram, option C, pressure entropy diagram, option D, TH diagram. So now I am drawing the diagram, and then we will see. So here 1, this one is 2, this one is 1, 2, 3, 4. So now I will draw the arrow for our clear understanding. So now let's solve this problem. Here 1 to 2, if you see, it's a isentropic process. So now the 1 to 2, if suppose on y-axis if we represent, suppose on the y-axis, if entropy, if on the x-axis, if entropy is there, then 1 to 2 will be a vertical line, but it's an inclined line. So now it's clear, on the x-axis there will be a no entropy. So the C and the B options are wrong because they are representing entropy on the x-axis. Similarly, if we see 2 to 3 process, so 2 to 3 process, it's a constant pressure heat rejection, means from 2 to 3 the pressure should be constant. And if suppose on y-axis, if pressure is there, then 2 to 3 should be horizontal. But here 2 to 3 is not horizontal, but it representing the constant pressure heat rejection. So on y-axis there will be no P. So the option A is also wrong. So only the one option, that is TH, is available now. So the correct answer is TH. Now I will explain on the basis of this TH diagram. So on the y-axis it will be T, on the x-axis it will be H. If you see 1 to 2, that is isentropic expansion, and 2 to 3, it's a constant pressure which can represented by this constant pressure line on TH diagram. 3 to 4, we know that is a constant enthalpy process. So here on the x-axis there is a enthalpy. So 3 to 4 enthalpy is same, and 4 to 1, it's a constant pressure heat addition. So the correct option for this problem is D. It's a TH diagram. Now let's take another important problem which is asked in GATE 2005. GATE AME 2005. First I am writing the problem here. A vapor absorption refrigeration system. A vapor absorption refrigeration system. Refrigeration system is a heat pump. Is a heat pump with three thermal reservoirs. With three thermal reservoirs as shown in figure. As shown in figure, a refrigerating effect of a refrigerating effect of 100 watt is required at 250 Kelvin. 250 Kelvin when the heat source available at when the heat source available at 400 Kelvin. Heat rejections occur at 300 Kelvin. Heat rejection occurs at 300 Kelvin. Find the minimum value of heat required. Find the minimum value of heat required in watt. So now let's draw the diagram first. Here I am having 300 Kelvin reservoir. Here I am having the device. Here I am having the 250 Kelvin reservoir, and here I am having the reservoir of 400 Kelvin. So now in this question, refrigerating effect that is required is 100 watt. So the refrigerating effect is 100 watt is required. So now if we see this thing, the refrigerator device is working between 300 and 250. So first I will give the notation. This one is Q1, this one is Q2, and this one is Q3. Here this work done is useful in running the refrigerator. So now if I am considering the refrigerator between 300 and 250 Kelvin reservoir, so I can write the COP. So COP for this refrigerator, I can write that is T1, that is T2 by T1 minus T2. So T2 here, yeah, that is T2 by T1 minus T2. So here if you see this thing, so the lower temperature is 250. So according to our theory, T2 will be the low temperature 250 divided by 300 minus 250. So COP I can also write, that is nothing but refrigerating effect divided by W, that is work. So it will be equal to 250 divided by 300 minus 250. So work done in that case will be refrigerating effect, that is 100 into 50 divided by 250. So work done will come 20 watt. So by this way we can get the value of work done. But we are interested in the value of Q3. Means our primary interest, we have to find out minimum value of heat, because this Q3 is required for running this refrigerator. So we are interested in Q3. But right now we are having the value of work done, that is 20 watt. Now let's consider heat engine. Let's consider heat engine between 300 Kelvin and 400 Kelvin reservoir. So I am considering this heat engine between 300 Kelvin and 400 Kelvin reservoir. So now according to the efficiency, because we are dealing in reversible heat engine, so efficiency will be 1 minus T2 by T1. So here in that case it is working between 300 and 400. So first I will draw the diagram. This one is 400 Kelvin, this one is 300 Kelvin, and here the heat engine will work and it will produce W. So Q1, Q2. So this one will be T1, this one will be T2. So here I will write 1 minus 300 by 400. So the efficiency will come 1 by 4. 1 by 4. So now we can easily get the value of Q3, because we know in the problem the Q3 is mentioned here. So efficiency is nothing but W upon Q3. So 1 by 4 equals to W by Q3. So Q3 equals to W into 4. So W we have calculated 20 into 4. So it will come 80 watt. So the correct answer is 80 watt. The minimum value of heat required is 80 watt.